Hey everyone, welcome back. In this video, we're going to be looking at Theorem 1.4.4, and it can be found in Fundamentals of Matrix Computations in the book by David Watkins. If you're not using that book, it's fine. You can find this theorem elsewhere as well. So it says, let n be any non-singular matrix. Again, it's n by n, so it has to be square. And let A equal that same matrix transpose times m. Now, if that's true, then according to this theorem, then A has to be positive definite. We're going to prove this directly. We're going to assume the first sentence there that says M is any square non-singular matrix, and we're going to let A equal the product of that matrix and its transpose, and we're going to show that it's positive definite. Now, to show that something is positive definite, we need to do two things, which we're going to see. I'm going to outline them. This is going to be the outline of our proof, basically. So one, we need to show that A in this case is symmetric. So we need to show that A is symmetric. So show A is symmetric, and when we say show that it's symmetric, that means to show that A transpose is equal to A. And then two, we need to show the following property is true. X transpose times A times X is greater than 0 for all X, so for all column vectors. And also where X is non-zero. So we need to show that. That's going to be a little more challenging. I'll say that for last. But first off, let's show that A is symmetric. So we need to prove both of these properties in order to say that that A is positive definite. So proof. Start with the first one. Show symmetry, right? We're going to prove first one. So show symmetry. We'll start off with A. So we know now that A is equal to, what is A equal to? A is equal to M transpose M. Now what we can do is take the transpose of both sides. So we're going to do A is equal to M transpose M. We're going to transpose both sides. Apply the transpose. Now here we're going to use this property of transpose. The property is A, B transpose is going to be equal to B transpose, A transpose. Now you switch them around and you transpose them. And also we're going to use the property of A transpose times A transpose is equal to just A. So back to our argument. We're going to show that. So A transpose is going to stay the same. We're going to reverse the order. This is going to be M. And now we have the following. Transpose. And we can simplify this a bit more. So this is going to stay as M transpose times M. So now we can go ahead and bring the second part down. So we have A transpose is equal to M times M transpose. But if we look closely again by transitivity, we can see that A is equal to A transpose. Because now we have this part here and this part here. We have the following. We have that A equals M transpose M and A transpose equals M transpose M. So therefore, thus A is equal to A transpose. Right, so that's the first part. That's the symmetry part. Not too bad. Next up is a little more challenging part. We're going to show that this property here holds for all non-zero X column vectors. Right. So let's see. Hopefully you can still remember what we're trying to prove. So now show A X is greater than 0. So we're going to start off by saying let X be a real column and non-zero. Right, so that means that X is not the 0, 0, 0 column vector. Because as we're trying to prove this property, to show that it's symmetric, we need to show that it's true for non-zero vectors. Now, we have that this is true for non-zero vectors. Now, we can start off with the property. So X transpose A, X transpose, X column, these are vectors. That is going to be equal to, we're going to substitute A for what we were given, right? We were given that A is equal to M transpose times M. So now we have X transpose, and we're going to substitute M transpose times M times X vector. Now these two are being transposed, so we can put them in one. So we're going to have MX transpose and then MX here by itself. Now, what we can do here is do a substitution. Let MX equal Y. So now we have Y transpose, right? That's and where Y is a vector as well. So it's a vector times Y, right? This part becomes this part, and here we get that. Now, when we have a column vector times its transpose, this is going to be greater than or equal to 0. We have that from the previous video. Again, if you look in the playlist, there's the one before it. So it's going to be greater than or equal to 0. Now, the only problem is that the property states we need strictly greater than, not greater than or equal to 0. So what we're going to do is going to show that this cannot be equal to 0. The only way that this expression is equal to 0 is if Y is equal to 0. So let's assume Y vector is equal to 0. So then we would have M, right, X vector is equal to the 0 vector. Again, so far this is good, right? We know that it has to be greater than or equal to 0, but now we're just trying to show that it cannot be 0 and that it must be only greater than 0. So we have the following. We assume that Y is equal to 0, so we make the substitution. But now we have to remember something that they told us earlier. They told us that M is non-singular. M is non-singular. By definition, if M is non-singular, that means that the only way to make this expression equal 0 is, the only way this is true is if X is equal to 0. Because if you are non-singular, that means that the only way to the product can equal 0 vector is if the X vector here is the 0 vector as well. But we already established earlier that, we said earlier that X is non-zero. So we said that X is non-zero here. So we have a contradiction. Y cannot be 0. This cannot be true. Because the only way this can be true is if this is true, if X is true. But we said X is non-zero, so we can't have Y equal to 0. So Y cannot be 0. So therefore, this expression here cannot be 0. So it is strictly greater than 0. So to summarize everything up, we bring this part down here. Now we have X transpose A X vector is equal to, well, actually not equal to, is greater than 0. And thus we have proven that our theorem. So to summarize, let's see, we have M is a non-singular matrix and A is M transpose times M. We're trying to show that it's positive definite. We need to show two things. One, that A is symmetric, and two, that for any non-zero X, X transpose times A times X is greater than 0. Symmetry is pretty straightforward using the properties of transpose. Now the second one, I do want to summarize that one again. We start off by stating this is what we want to show. We let X equal a non-zero vector. We start off with X transpose times A times X. We substitute in what they told us A is, which is a product of M transpose times M. We group these two together. We group these two together, and we applied the definition of transpose, but in reverse, the one we did up here, but in reverse. So we group them together, but now we have two matrices, and we say let Mx equal Y. So now I have Y transpose times Y. On the previous video, we saw that a column vector times its transpose can never be negative, so it's always greater than or equal to 0. So that was good so far because we now established that this is true. But now we need to show that it is strictly greater than 0, right? Because our definition of positive definite states that it has to be greater than 0. Not greater than or equal to, just greater than 0. So we go off to the side and we say, okay, let's assume that y is equal to 0. So we get this expression here. But m is non-singular, so that means that if you have m times a vector and it equals 0, then the only way that can occur is if x is equal to 0. But there we have our contradiction because we assume that x is non-zero. So the only way that y can be 0 is if x is equal to 0, but we established that x cannot be 0, so y cannot be 0 either. So that means that this expression can never be equal to 0, it can only be strictly greater than 0. And then by transitivity, this expression is strictly greater than 0. And that is a definition of positive definite, and we are done. If you found this video helpful, please give this video a like and subscribe, and I'll see you next time.